Good afternoon, everybody. I hope you enjoyed lunch and our quick break. Kish Rajan did a great job with his presentation this afternoon. He mentioned my name 3 times, so that's a real plus for me in IVEDC. I work very close with the governor's office, and I think that this topic that you're going to be listening to today is very relevant. You know, as we talked about energy storage in the past, it was something that we thought would be needed, and now it's mandated. And so it's truly the time has come. And as we've gone through developing these conferences, we always want to look at things that are relevant. And it's really interesting how, just in that planning process, how things evolve. And so we think this is a great topic. Your presenter or your moderator today is going to be Laura McDonald, who I've worked with quite a bit over the years. And I'll never forget the time when she was working on the Sunrise Power Link that we had a speaker at Rotary. And there was a question. After he gave his presentation about the Sunrise Power Link, somebody said, "What's in it for us?" And he's a little confused, and he said, "I don't know, jobs and taxes." And so I always remind Laura about that. And Laura's moved on after completing that project, several other projects, but her new project, which she'll talk about a little bit, has to do with she's now the expert on electric vehicles. And we have some examples. As a matter of fact, the magazine that we put out, we have a picture of the Tesla site that's at our regional mall here. So your moderator today is Laura McDonald with San Diego Gas and Electric. Has been a great supporter of IVEDC, a great supporter of this conference. We're glad to have her here talking about a new subject which is very relevant to the Imperial Valley. Thank you, Laura.
Thank you, Tim. I was a little nervous when you said you had a story to tell. We have a few we probably can't tell out loud. Well, welcome. Thank you so much. I feel like I've come full circle out here in the Valley, having started many years ago working on the Sunrise Power Link, and then working on many of the renewable projects we have today that are utilizing the Sunrise Power Link. So for those of you who heard Jim Avery's speech last night, we're very proud of the 1,000 megawatts we have flowing across the Sunrise Power Link, thanks to many of you who are here whose projects are utilizing the transmission line. And now, in my new job as the Director of Clean Transportation and Advanced Technology Integration, which used to be our Smart Grid group, and we've changed the name and have a little bit different focus, but I have the pleasure now of working on all things clean transportation, electric vehicles, natural gas vehicles, and energy storage. So I was thrilled when I was asked today to moderate a panel where we can bring those two subjects together. And so I am pleased today to introduce our panel, and I'm going to try and turn this down a little bit. But I guess I just wanted to start off by saying that we do have a unique opportunity right now, not only here locally, but in the state of California, to figure out how to bring together renewable energy and energy storage. And here, particularly in the Valley and in San Diego, the opportunities really are endless. And so I'm pleased today to introduce our panel, and I'm going to start out with Rob Ferber, who's the founder and CEO of Electron Vault, Inc. Rob has over 10 years of experience pioneering the use of battery technology. As science director at Tesla Motors, he was responsible for the company's early development of the lithium battery packs. At Electron Vault, Ferber and his team are focusing on low total cost ownership of energy storage systems for fixed base and mobile applications. And Rob, as a proud owner of a Toyota RAV4 all-electric with a Tesla battery and a Tesla drivetrain, I just want to say thank you. I love my car. So welcome to the panel. And next, I'd like to introduce Kate McGinnis. Kate is responsible for the energy storage project and market development in California for AES, one of our fun partners. Prior to joining AES, she led development of stationary storage projects co-located with oil and gas infrastructure for Chevron. While at Chevron, she was also involved with the development of renewable projects, including geothermal, solar thermal, and wind. And Kate has been involved in the energy industry for over 15 years. So welcome, Kate. Our third panelist is Mark Pinty with the Imperial Irrigation District. Mark serves as the Energy Systems Operation Manager for the Imperial Irrigation District. He manages and provides strategic direction for IID's energy system operations, including transmission and distribution operations, generation balancing, open access transmission, energy management, electric systems, cybersecurity, and customer service restoration. My goodness, it's quite a resume. Mark has been with the energy industry for over 25 years, so welcome. And last but not least, we have Tracy Sizemore, who's the Vice President of Development for Symbol Materials. He's over 25 years of multinational experience with various multinational chemical companies, has a strong background in strategic planning, business development, global operational health, safety, and environmental and security experience, and served as the property risk management with Phillips Petroleum and ConocoPhillips. So welcome to all of you. And I think today we are going to start with Rob for your presentation.
Okay.
You can either sit or stand, whichever you prefer.
Okay, how do I do the events?
That is a fine question.
Oh, thank you. Modern tech. Well, thank you for that introduction. It's always nice to have a happy customer starting to say something good about me. It also brings to mind, though, the fact that this is a space where you've got a technology that's in transition. When new markets open, when new technologies arrive, they go through a sort of a birthing process, a childhood, and then they reach some sort of maturity. And at that threshold where they go from demonstration projects, proof of concept, and technical engineering projects, things that are backed by grants, things that are backed by, shall we say, non-market force fund sourcing. You get the transition to the things that simply have to make it on their own in the market, in an unsubsidized market. This is the critical point where a market can go dead or can become explosively growth. The storage sector is at that cusp. And there's several paths in front of us. And one of the critical challenges for storage is to not ask, what are all of the problems we have with the grid today? And asking, can I make storage solve it? Because that's a technical question. Of course it can. The question that I think is more important is what is economically possible within the legal and contractual frameworks you live in. Because either you need to change those or you need to live within them. And this is the critical part for actually being a business instead of being a research project. This is something you will see again and again as you examine and look at other storage projects and individual products. And so, without more on that particular soapbox, okay, the first few slides I'm going to go through quickly. This is all stuff you probably essentially know. One of the problems you have with renewables, two in particular, wind and solar, is that they can ramp faster than any other generation resource on the grid. As a result of that, it's very difficult to have the grid, the conventional resources, track the variations in the renewables. This is the largest challenge, actually, for renewables integration. It's not time of delivery. It's the speed with which the outputs can change, and integrating that and matching that with conventional resources. Another thing that comes with storage is there's a lot of perceived risk. There's perceived economic risk, there's perceived safety risk. Something I used to do, but which I have been discouraged from doing in recent years, was when you went to a venture capitalist and you were doing a pitch for your company. You'd bring in some materials typically for a little bit of show and tell while you're giving the business pitch. Bringing a bucket of gasoline into a venture capital pitch is probably not the safest thing in the world, but it certainly gets their attention. Everyone's afraid of it. Why? Because it's sitting there in a bucket. It's not an engineered system. It's extremely dangerous. The difference between that bucket of gasoline and what's in every car, or very nearly every car, out in that parking lot, is that those cars have got 100 years worth of engineering on how to make that safe, manageable, useful. Battery systems need to have that same actively engineered safety considered into them. They need to be compatible with the technologies of today, and they need to be something that can be carried into the future. The time scale of grid and utility applications is much longer than your conventional business installations. You know, leases last 5 years, grids last for hundreds. You've got to exist in the real business world too, so your cost of acquisition, cost of ownership, maintainability, all of those things have to be there. Yeah, so I believe I've got more lithium-ion battery systems deployed, large ones, worldwide, than any other human. The number is actually approaching 3 gigawatt hours. We've been at this for a while. Okay. What is a battery system? Now we get to the fun stuff. You know, a lot of companies look at the cells and they say, oh, the cells are safe. The cells are safe. Or the cells are not safe. By the time you've gotten to a battery system, that is always a lie, whichever way you say the answer is. One of the things that's fun to do when you've got something the size of one of these tables that can deliver a megawatt is put a new engineer in a room with it and have something go bang. And then you turn the lights on and ask them, what was it? Some of them will say, well, a battery exploded, clearly. And then they show them the stubs of the copper wire, the 1-inch diameter copper wire that blew up. And they get very quiet. Copper doesn't explode. But these battery systems are capable of delivering energy and power densities that are entirely outside of ordinary experience. They're not part of what most people are used to dealing with. And so the risks and the hazards stem almost entirely from that. The flammability or explosiveness or any other aspect of the cells themselves is entirely secondary. You do need to engineer so that there's no chain reaction failure modes. But, like I said, this is a game of engineering. And the system consists of energy storage elements, the cells, the batteries that most people think of, plus management systems, plus support systems, plus a way of electrically connecting them. We have innovated in all of those things. There's no wire inside of our boxes, for example. Don't like it. Guaranteed point failure. One of the things you see, since this is a young industry, is there's not a lot of installed stuff out there. And so you find that systems tend to be very, very large, very monolithic, and a kind of one-size-fits-all. Here's your 1 megawatt hour box. This isn't responsive to the market. You need something that you can have a fairly fine granularity of scaling. You need something that can be expanded. You need something that can be maintained. And if you have to take portions of the system down for maintenance, it should be able to be done while it's alive. These are all things that we've engineered for, and they're important and critical to the customers that are paying for the services the product can provide. Now, I mentioned this earlier, but this is one of those things where there's theory and there's reality. A lot of people look at solar output curves, like the chart on the left, and say, well, here's from geometric considerations what you might expect the output of a solar farm to be with, say, fixed panels. Yeah, that's nice. It's completely fictional. There's nowhere on the planet you can get that output curve. The chart on the right is what you actually get for a site in Pretoria. These are both models for the Pretoria location. The chart on the left has the advantage, though, of if you're writing a contract to provide power, you can probably get paid for the chart on the left. It's predictable. It's smooth. It's not varying too rapidly. Unfortunately, the chart on the right is what you actually get. And the challenge here is, how do I monetize that? You know, this morning we heard that current solar PPA contracts in California are going for something like 4.5 cents per kilowatt hour. One of the reasons for that is because behind the scenes they've got to figure out how to fix the deficiencies, the problems, the quirks of the solar output, and that costs money. You know, a new geothermal plant could go for 11 to 12 cents feeding into the same grid, and the difference is that the geothermal is available 7 by 24 and is smooth and is predictable. The addition of storage to the solar allows you to render the one into the other. And the question is, can you do that within the price spread that the market is showing right now between conventional solar and other renewable resources such as geothermal? Rendering the curves smoother and more predictable is the key part of this. You don't have to move the power into a 24-hour delivery window. You just need to make sure that you can ensure that your ramp rates are compatible with the other mix of generation and dispatching resources that are on the grid so that you're not moving faster than anything else can keep up with. You don't have to move your solar into a 7x24 model. You do need to make it something that can play ball with the rest of the generation resources and the loads that are on your grid. And so understanding the requirements for local ramp rates is a critical piece of designing the solution for any given application. You know, California, we've got a lot of desert. We've got a lot of very sunny places. It's unusual. Much of the world is, shall we say, much cloudier. As they say in Boston, if you don't like the weather, wait 5 minutes. Yet there's megawatt photovoltaic installations all over the eastern seaboard. In many cases, they cause grid problems. One of the reasons for that is they can bounce up and down very, very quickly. And while you can control the rate with which a solar farm output rises just by controlling the controllers, the inverters, you cannot control how quickly it drops in its output unless you have storage. As an aside, Electron Vault tends to put its storage on the DC side. So with conventional AC coupled storage, whatever goes into the storage system has to go through 2 cycles of power electronics, and you often lose 20 or 30% of it in that cycle. You typically lose 1 to 2% of your energy in an Electron Vault system just because we're on the DC side. And in fact, because there's often less inverter than you have solar panel at a typical installation, we can actually increase your output in some cases by 1 or 2%. So it's all about ramping events. You don't want every cloud shadow causing your output to drop, and then every time the sun comes back, you get a double whammy. People talk about cloud edge effects. It's true, but it's not the real issue. The panels cool down in the shade. When the panels cool down, their output, their efficiency increases. So when the sunlight comes back on, and when the shadow goes away, the output of the panel rises very, very rapidly and to a level higher than it was before the cloud shadow event because it's cooled down. So you get these extraordinary spikes when you get clouds abruptly leaving a site. And you get these extraordinary dips. You can see slew rates of 20 megawatts a minute, 50 megawatts a minute commonly. There's very few things on the grid that can move that quickly. This is a particular graph for El Centro. We're here in the desert. This is about as good as it gets. And even here we had over 1,200 unplanned ramping events in a representative year. This plot, I should explain, I'm sorry. The horizontal axis is the day of the year. Day 1 is on the left. December 31st is on the right. From the front edge of the chart back to the back edge is the hour of the day. So this shows every day of a year. Morning is in the front edge, noon is at the middle, evening is at the back edge. And this is showing the amplitude of the unplanned ramping events. For some of the sites on the East Coast, we're seeing 12 and 15,000 of these a year, not 1,200. This is for Santa Rosalia, across the border with our neighbors in Mexico. A similar large number of unplanned ramping events. This can cause frequency control loop problems. This can cause your grid frequency to wander rapidly and dramatically. And it can trip some of your control and safety systems off. So it can actually trigger blackouts if it shuts down a diesel genset. So it's smooth the curve, but more importantly than smoothing, it's control the ramp rates so that you're not moving faster than the other things that are on the generation mix. That way there's other things that can fill in for you when you ramp down. And you can ramp up in a way that's graceful in allowing other things to ramp down. With the typical SunVault 1000 type installation on the DC side, we can completely eliminate unplanned ramping events for any site in California or in Baja. We are able to reconstruct for the space age period generally at 1 minute, 30-second, 5-minute, fast data intervals. What the solar radiation at the surface of the Earth was almost anywhere on the planet for almost any year in the past 20 or 30 years. This allows us to predict behavior and to compare actual behaviors at sites with what was predicted and with what the weather is giving you, which allows us to spot problems on existing sites and accurately predict what will happen at new sites. Another thing is you don't build solar arrays out of 1 megawatt solar panels. You build them out of 300-watt panels. You build them out of a lot of them. If you have very large battery systems, they become things that fire marshals are not fond of. They become risks. We use distributed storage farms. We use the same industry standard panel connectors and wiring. We go into your combiner boxes just like the panels do. You can integrate a partial string, a complete string. It's very gradational. It's very granular, and it allows you to scale or change the scale of your system, in most cases, very rapidly. Also, from a permitting perspective, it's very easy. These are small structures that are ground mount. They're not human-occupied spaces. If one of them catches fire, it's isolated. You're already in the middle of an area that's free of vegetation at a solar farm. They typically go under the panels or near the combiner boxes. And delivery is typically 90 to 120 days after the signing of a contract, not 18 months. We were forced to work internationally because of the economic models for the businesses in the States when you're doing storage. We can recover all value streams in most of the markets in Africa and Asia and Europe. And there are some difficulties with that in California and other parts of the States. So we actually have more hardware overseas right now than we do in California. But the situation in California is evolving rapidly, and there's now a large number of economically viable applications here. So we've returned to the state and are rapidly expanding our footprint here. Appreciate your time. I think the questions are at the end.
Yeah, please. Rob, thank you very much. As you can see, we have, thank you. Thank you for the introduction to that. As you can see, we have tremendous opportunities and I think challenges along the way, right? I spend a lot of time these days on energy storage up in San Francisco at the Public Utilities Commission, and I think we're all trying to find out exactly what energy storage means in the world that we have today. And I think we have tremendous opportunities, so thank you very much as we move forward. And I'm now pleased to introduce Kate with AES. It'll be interesting to get the developer perspective as we move forward as well, so thank you.
Thank you, and thank you to the Imperial Valley EDC for having us today. So I'm going to tell you a little bit about AES. I'm going to talk about our projects and the business drivers for them, and a little bit about what's next. Is this it? All right. Legal stuff. So AES has a global footprint, and our goal is to improve lives by providing safe, reliable, and sustainable energy. We're in 19 countries, and we have 36 gigawatts of generation, and we actually own 8 utility companies. Lots of different fuel sources, lots of different locations. In California, we've been here since 1987, and which was pretty early. The company was founded in the early 80s. We have natural gas plants, renewable energy, wind, and early on we were the developer of the Mount Signal project, although we have exited the solar business that we had here. We're also California's largest battery energy storage developer. So, on to the projects, which I think is what you really want to hear about. We put the first grid-scale lithium-ion battery on the grid in 2008. That was at Indianapolis Power and Light, which is one of the utilities that AES owns. Since then, we've taken that and taken the learnings from that and deployed them into commercial scale projects in 2 main regions. In 2009, we put the 24 megawatt resource in Los Andes, Chile, and have followed that up with 2 additional projects in the northern part of Chile. We also have completed 3 projects in the PJM grid in northeastern US. So, batteries on the grid? Yep. It's battery cells, so much like what you see in a laptop, in your tablet, and they are packaged up into modules, then into trays. They go into racks. The racks look a lot like a data center if you've ever been in one of those. And then they're put out in storage arrays. They can be in a container like you see here. We're also now starting to build battery systems in buildings. And so that really will depend on the size of the system, whether you go for containers or buildings, as well as the location. So our first commercial project, we started in 2008. It's in the desert in northern Chile. The grid there, it's a remote grid. It's fairly small. And the commercial application of this project is for spinning reserve. You can see the location there. It's near the base of the Andes. Here's another picture of the same resource. It provides 24 megawatts of resource to the grid. And we followed that up a couple years later with a project, a second project in the Andes. And this has won 2 awards. One from Edison Electric Institute in the international category, a second from Power Magazine as the plant of the year. So this is co-located with a coal power plant and provides spinning reserve. Then we moved into the US. We've built a project in Laurel Mountain, West Virginia. It's co-located with 98 megawatts of wind. And this project is primarily providing ancillary services, frequency response to the grid. Followed that with our Tate battery. So this is in Ohio. And much the same like the ancillary services model in West Virginia, here it's co-located with a gas plant. So, on to the future. Why will utilities want to put energy storage onto the grid? Well, there are definitely increasing demands from renewable targets, and you heard a lot about that. You can definitely control that at the location of the actual generation. It can also be controlled more centrally, where potentially some of the variation from the individual locations cancel out to some extent, but the ancillary services are still needed. In addition, over the next few years, we're expecting a lot of retirements of peaker plants and other conventional generation. Rather than replace that with new peaker plants, you could use energy storage as a resource. And I'll get to another slide that has some reasons why you might want to do that. Here's a little bit more. So energy storage is always on. When you use a natural gas plant, for example, as a peaker plant, it's going to run, 6.6% is the average of the time. Energy storage is going to always be on. It can provide ancillary services during the non-peak times. It can help the grid in ways that a peaker plant is unable to, because when it's not on, it can't do anything. Energy storage is also very flexible. We can do maintenance on a very small piece of a project at a given time without having to take the whole thing offline, or a large portion of the project offline. So rather than, say, maybe a 3-unit gas power plant where you'd have to take a third of it offline, we can take a much, much smaller percentage. There's also, in various parts of the world, drivers that are coming from the regulatory point of view, and certainly we see that in California, both coming from kind of system needs as well as interest from the larger populace and regulators. Most recently, AES won a 200 megawatt resource project in Southern California. It'll be 100 megawatts interconnected, which can provide, if you're starting from a charging scenario, it can make a flip of 200 megawatts in one instantaneously. It's going to provide local capacity. It'll be a 4-hour duration, and there are no emissions or water associated with the project. All right, thank you.
Thank you very much. And now I am pleased to introduce Mark with the Imperial Irrigation District and to give the utility perspective. And let me tell you, Mark, I know you know this, the utilities grapple every day with how we bring energy storage into what we're doing today. I think just quickly, you know, when the Sunrise Powerlink came into service and the San Onofre nuclear power plant went out of service, I think we all sat back and said, what do we do now, right? Sunrise came into service right in time, but going forward, and I think that every day we look at energy storage, electric vehicles. I think the reality is, and I know not a lot of people want me to say this out loud, I'm not sure what the future of natural gas fired power plants going forward will be. I'm not even sure if we'll see another major electric transmission line built. I mean, I know it's not popular to say that. We spent 9 years trying to get the Sunrise Powerlink built. So I think between electric vehicles and energy storage, it might be the only new infrastructure we see being built in California going forward. So welcome, Mark.
Thank you all for coming this afternoon. This is really exciting for IED on the battery storage. For almost 4 years, we've been looking at a battery system. I was asked to come today to talk about the applications for balancing authority grid operations for the battery storage. We've heard this morning, and you've heard from many keynote speakers, the interesting part of solar, wind, or geothermal, integrating it into a grid operations. Geothermal we've had around for a long years, had a good relationship with them. Their outputs are pretty well strictly to their schedules. Solar and wind, however, since they're mostly more susceptible to cloud cover, less wind push, you see a lot of erratic output. So on the grid operational side, we have to balance that. So therefore, either we have to put on a lot of expensive units they have on spin to react to those type of contingencies. So to jump right into the, we'll just look at the effects of solar integration on a balancing authority and intermittency, and then we'll dive right into the application and benefits of battery storage facilities for balancing authority, providing reliability efficiencies and potential economic benefits. IED here in mid-2015, for our own load serving, we'll have roughly 135 megawatts of PV solar, and at this time we're roughly exporting 150 megawatts of solar out. Therefore, IED will need increased efficient ramping capabilities, and the picture you see on the slide there, you can kind of see how the solar intermittency is all over the place. It's just a characteristic of solar. I know we're mostly talking about solar, but wind also has the same characteristics. Geothermal, on the other hand, has very limited characteristics to these. This is a graph here last August on days the 15th, 16th, and 17th. And as you can see, it starts out at 6 in the morning and goes till 1900 at night. And this is a scale of just showing zero output with their schedule and whether or not if they overproduce or underproduce. And as you can see, the erratic can go pretty deep throughout the day, which our generators are constantly chasing this and bouncing for it. The next slide is looking at it from the output of the solar throughout the day and just the up and down without the zero platform, and that's also in the same days, the 15th, 16th, and 17th. Earlier, Kevin Coffey alluded to some of the things we're trying to do in grid operation is using the 15 market window in the ISO right now to kind of help with some of these. The other areas that we've done is work heavily with some of the scheduling units and other stuff to try to work out these ramps and handle that way. However, if you put the same grid on a 4-second scale, you would see that everybody thinks that solar has got this nice smooth load profile. However, on a 4-second, you'll see that it is just constantly moving. And it's just the characteristics of the solar rays and other stuff hitting the panels. So we'll go ahead, I guess, I'm not sure why we're missing a slide here. Anyways, this blank slide had a graph on it. And what this was representing is one big thing, especially for a grid operator. We have standards that we have to follow. So we're being constantly monitored, our CPS values. And with solar integration, we have been seeing over the last few years our CPS decline. However, to overcome that, we put on more generation units to help with the ramping capability to smooth out the CPS to make sure that we stay within the standard requirements. However, the slide kind of showed on a analysis that we did of it, how if we didn't put other units online or come up with another solution such as battery storage, that we would soon be failing CPS violations and probably would be fined FERC, and they'd ask us what was going on. So anyways, going into the operational application benefits of the BESS, batteries, if you see the characteristics of it, they have quick response. Put there, you can see there the turtle and the rabbit. The battery is going to be a rabbit. I mean, it's fast responsive. It can do whatever you want. I mean, the applications you can do is endless with a battery. Your fossil fuel units, yes, they have good ramping capabilities. However, they're just not there the same as a battery. As you can see, ID's unit average ramp rate with our units is 2.9 megawatts a minute. With a BS ramping rate with a new battery that we're going to be looking at getting into, and we're showing up a vendor right now, is going to be in roughly an area of 27 megawatts, 0.03 seconds. So you can see how quickly it can respond to these variations of the solars to smooth this out, which also dramatically helps our CPS and our reliability balancing and other areas. The other applicational benefit is with a battery is integrated into our SCADA EMS system. Therefore, we'll be able to do many applications, multiple settings to provide customization performance. As you can see, SCADA, the biggest part of this with the integration of solar is going to be the ACE following, which we can set up key parameters and set points in there. So in other words, instead of our units trying to follow these, our units can be more stable where the battery can interact to them. Also, we can put in forecast data and other stuff into our EMS to automatically fire these batteries before they even starting to see the ACE deviations. The other part of the battery that we plugged into there, we can set up parameters around our voltage, frequency. The other key elements is you can also put in RASs, special RAS schemes, where you lose elements, different parts of the line, where the EMS will automatically send signals to the battery to go ahead and either absorb, push out, provide VARs for us, do all kinds of applications. Lastly, the biggest component, because anytime you get into a battery, there's always a cost component to it, and we need to sell it. So when we looked at the battery, what we're going to do is utilize the spinning component of this. And as you can see, typically with your gas units or any unit that we have online, we're going to have a poor heat rate compared to the battery, expensive gas, even though gas is going then down. Unit must idle there and be with no load. So, I mean, you're going to have all these operational maintenance costs and everything for a unit to sit there and just sit and just wait to respond. And also, it also affects our carbon footprint, especially in California with the carbon caps and other stuff. This would be a good reason to get a battery because we can also use that in that area. So anyways, the results of looking at these things is very expensive capacity without a battery storage to can deal with the intermittency. Here we can kind of show on the BS provides spinning reserve capacity resulting in shutting down units for significant periods of time. Now the big thing for us, especially on our load profile for IED, the summertime, that's when our peak load is. We're going to have all our units online, the solar is going to be online, and it's not as hard. However, in our winter, when we drop down to almost 30% of our peak load, and all of a sudden we have numerous amounts of solar on, we're going to have a way of shutting down our units, but this battery will be able to sit there and either absorb or put out. The other big thing about the battery is that oft times throughout the 24-hour period, we can charge it with really inexpensive power, or we also can buy power out of the ISO. Well, actually, they'll pay us to take their power to charge these batteries on the way that their market's structured. So there's a lot of possibilities of beneficial economic benefits to have this battery. It also reduces the carbon footprint because we're not running units or fossil fuel units. Also going into the voltage and frequency controls, this will add capacity to our system with the battery, increase response, and reduce outage time. And the reason why I say that is if you look at, we went up to Fairbanks, Alaska, and the main purpose why they put their battery on is many times they had 1 to 2 lines going up to Fairbanks out of Anchorage. And when they lost those lines, they'd have to rely on their gas units and their oil units. And most of the time, they'd have to leave them running because if they went out, then you'd be black starting everything. You have to shut everything down to start it back up. So to leave those running is very expensive. So they went ahead and put in a battery system, what it is, 10, 15 years ago, and they saved their customers millions and millions of dollars by shutting those units down. Because what the battery provides for you is during an outage period, say you lose a unit, say you lose a line, or you don't have imports coming in, we can wrap that battery up, cover that GT unit while we're starting up the GT unit or maybe a heavier unit to come online and cover those contingencies. That way we don't have to sit there and have them run 24/7. This is just a slide going on what I said, starting up the quick start units and reducing and eliminating outages. So in conclusion, the effectiveness of balancing the PV intermittency, providing additional capacity for a BA system, helping absorb or produce when ACE is imbalanced, provide energy to the system as spinning reserve, reasonable operating maintenance costs, provide reasonable response time for BA to make the best operational and economic decisions, decrease outage events, and potentially shut down of units for significant periods of time. So these are some of the aspects we're looking at. In no way any expert into the battery storage area. Like I said, we're very excited. We'll have our battery online by December of 2016. So we're very enthused to go ahead and work this into an application of a grid operation. I think you're going to see this go across the nation where more utilities are going to put it on their side of the fence. As we heard, on the other side of the fence of the subs for the solars and those type of things, they already have them there. They've even done it for customers on small base for houses and that type of thing. But for grid operation, this is going to be a great potential for us, and I believe it will definitely help with the balancing of the integration of green power. Thank you.
Thank you, Mark. And now, last but not least, pleased to introduce Tracy Sizemore with Symbol Materials.
So if you've ever been to a family reunion and you get back and you look at the family photos and you think, who's that kid over there? Because he doesn't look like anybody else, that would be me. Probably wondering how I fit into battery storage or this whole process. We are the things behind the battery storage, and behind the batteries, we produce the materials that they need to manufacture the batteries. So we're big fans of battery manufacturing. So buy more lithium. Okay, let's start off here. Imperial Valley has a vast resource of a variety of recoverable minerals in the brine. We've been able to demonstrate the recovery of lithium, manganese, zinc, potassium, rubidium, cesium, and there are a number of other things on our targeted list for recovery. As a company, we decided to start our first project on lithium. Primarily as a startup company, it's the best return on capital, and it's a good market to enter into at this time. But there's plenty of other commodity products to go after. We are very symbiotic with an existing geothermal plant. It saves us a lot of capital to not put in a production well, reinjection well. We work well with them. And in the process of removing many of those materials from the brine, we lower their cost of reinjection, the well treatment, and we help sustain the longevity of the formation by removing the things that would otherwise be plugging it. So we're a good addition to them. We tack on the backside of the plant. They typically will deliver brine to us somewhere around 110 to 105 degrees centigrade, which we love. And so it's a very good relationship. The first project in Imperial County on a minerals project was in 1950. There was an application for a potash company to recover potash from the brine. Over the years, there's been a lot of trouble in doing mineral recovery, primarily because of silica and iron. They have a tendency to scale and coat everything. These are examples of some pipelines with ferrosilicate glass that forms on the inside. And so as a result of that, it inhibits mineral production. It's a very costly process. So we have 59 patents that are 19 that are issued and several that are pending. And one of those patents is how to remove the silica and the iron from the brine in the Salton Sea so that other minerals can be produced. So that's an effective part of it. If we look at our major competitors in the lithium world and you look at their supply chain, when you're talking about carbon footprint, this was a good example of one of our competitors. They take soda ash from Wyoming, they take it down to Argentina and Chile, where they do some of their primary manufacturing. They then take it up through the Panama Canal over to North Carolina for processing, and then roughly 92% of it is shipped across the U.S. over the Pacific Ocean into Asia. So for us, that's about an 18-month logistic chain. We're about 6 hours from the wellhead to a completed product. So our ability to move with the market is much higher. We can produce lithium chloride, lithium carbonate, or lithium hydroxide. We can fluctuate very easily with the market demands. We're all in one location, and so there's a lot of cost efficiencies associated with that. And probably the other big savings with being with geothermal, compared to some of these other operations who have to heat their brine to treat it, we start off with heated brine to begin with. So there's a huge economic savings as a result of not burning natural gas to heat your brine up. This is an example of the lithium market and what it's used in. There's a variety of products that are made with lithium. We've focused primarily on battery-grade lithium products, and for both market reasons and complexity, have chosen not to enter into some of the other markets. This is the global demand for battery-grade lithium products. As you'll see, Asia dominates the production of cathodes and batteries, and so that's the predominant market to that. We took one of the car companies' estimates for their demand for lithium, and we plotted those on the chart. That's the lines above that is the high and low of their estimate, and the dashed line is their average. So if you look at the effective industry capacity to produce, you'll see that there's a big difference between supply and demand. So that's a favorable time for us to enter into the market specific to that. Well, missing a couple of slides there. That's fine, we can just talk from there. So So as we're underway in our development, we have completed all the testing. We're starting our design for commercialization and construction of the plants. The Imperial Valley has the capacity in the existing geothermal plants to produce 150,000 metric tons of products, of lithium products for grid storage batteries, car batteries, any other kind of batteries that want lithium, manganese, zinc into them. And so our first plant will enter the market at about 10% of the current demand. But as you look at what the stated demands are for the various companies, their demands are more than the effective capacity of the industry times 3. So there's a huge market looming supply-demand need that will allow for a rapid growth in this industry, and especially in this particular location. So I'll wrap it up with that.
Thank you very much. Now, we are going to go to audience questions, but I wanted to just ask a question of all of you, because I think the big question is really from a policy perspective, especially at the state level. And so while we have AB 2514, and certainly the Public Utilities Commission's interest in energy storage and the mandates that the utilities have, I guess I was wondering if this is enough, and what we have today, to really jumpstart energy storage in California, or what else maybe needs to be done on a policy level. You know, of course, we have the governor's interest and a lot of the elected officials, but what else, from your perspective, should we all be looking at from a policy standpoint to ensure the success of the energy storage market? And you guys can sit here and use your microphones here for any of you that want to weigh in on that.
Well, if I could start with that, one thing that is very important, I think, for this market is end-of-life issues. Making sure that there is a safe, economically viable, and rational recycling and disposal route for lithium batteries and all energy storage elements as they reach their end of life. I spend a lot of time outside of the U.S. You know, I've seen people burning copper wire in the street just to burn the insulation off of it so they could get clean copper that they could sell. This isn't what we want to have happen to the energy infrastructure of our state as it ages. We want to make sure that there is an economically viable, safe, and sustainable method of recycling all of this. And so this is something to use as you're guiding which technologies get deployed. I think, you know, all of the ones here are compatible with that. But it's something to consider, because not all of the products on the market really have an obvious path to end-of-life disposal.
I guess let me touch on that really quickly. When we, sorry, is that better? Okay. When AES procures the batteries for its systems, we ensure that we're working with reputable suppliers that will have recycling available for the product at the end of life. As far as policy goes, I think it's really important that storage is allowed and able to compete head-to-head with other energy sources for the types of procurements that it can do well technically. And I think that the prices and the benefits of storage will bear out in those types of procurements. So, you know, I guess I'm not necessarily asking for a specific policy, any kind of mandate, but the ability to compete and be valued for its benefits.
Well, I can say this without going into too much detail. We have our all-source RFO out on the street today for San Diego Gas and Electric. We have a lot of interest. And I think that for us, it was heartening to see how many companies are interested, how many different technologies are out there, how many different ideas people have for energy storage, and how we tie kind of our renewable energy future into energy storage. And I think one of the things that we're all looking at, and I think that not only the County of Imperial, but the County of San Diego and all counties will look at, you know, siting issues and community issues, because this is all new to us. And so as we move forward, I think it's a big learning experience for all of us. I think in our case, the Public Utilities Commission is watching that closely, but we want to make sure that it does not take years and years and years to get these projects sited and operational. And so to the extent that you all can help us, and we can make sure that our policymakers on a local, state, and national level understand the importance of these projects, because if it takes as long to get energy storage projects sited and built as it took us to get one transmission line built, we probably are not in a good space. But I'm hoping that we can find a way to do that, certainly more efficiently. So anyway, I wanted to open it up today to anybody who has questions, absolutely. And I have a microphone.
Thanks for the presentation. I'm Tim Duane. I'm an attorney, but also been a professor who's worked in this field for a very long time, not on the storage side, but more on the renewable side. I've written a lot about integration, and I'm struck by, Rob, you began with a comment about whether or not the legal and contractual structure would accommodate the technology. You also talked about the notion of transitions. And Kate, when you talked about a series of projects, you mentioned spinning reserve, frequency control, the like. And then Mark, you talked about the ramp rate, as Rob also suggested, was really the more important issue. So following on Laura's question, how can we structure the market to incentivize the proper ancillary services that storage can provide? Because as we move toward a higher penetration of renewables, the integration issues become more important, but we need different things. We heard this morning John White comment on how we're valuing peak of the afternoon solar when that's the problem, not the solution to that particular problem now. So if you could comment, anyone on the panel, about how can we structure these markets so that you know what you're getting value for?
Okay, so one of the things that's interesting about storage is it can look like generation, it can look like load, and it can look like transmission. And those three bins are regulated differently and handled differently. And so that's one dimension of it, having a simple legal structure that fits into the ISO model that can be any of those things. I mean, the California ISO has a website, and on it you can see the real-time nodal clearing prices for California. And if you watch it for long enough, you'll see a whole bunch of events where you lose a transmission or a distribution segment. And on one side of the failure, prices will go to $1,000 a megawatt hour on the spot market. And on the other side of the failure, you'll find that prices go badly negative, maybe minus $100 or $200 per megawatt hour. That's the spot market. But it is showing that there is a need to support the transmission and distribution system we have today, because building a new one I don't think is financially in the cards. But yet you need a financial mechanism for having a battery that can be transmission deferment, transmission peaking management, not for total demand, but for individual transmission segments. And right now, that's extremely difficult to get a contract written that monetizes it.
Anyone else?
Yeah, I'd just like to say, I mean, to go to your point, to see more battery storage on there, I think with some of the standards, newer standards that are coming out, particularly balancing standard just came out recently, where FERC and NERC and WEC put it back on the balancing authorities to make sure the proper reserves were carried for generation. And I think when that pushback got there, we saw it on our side, and I think the ISO who's ever here in San Diego to even talk about that. What we had to do is on a lot of our units, even geothermal, we went ahead and dynamically scheduled them out of our system into the ISO. So now the ISO has got to go ahead and balance for those generation instead of us balancing for that. Now the ISO is fitted with the burden to do that. Now if they're fitted with the burden to do that, they might now start looking towards battery storage, those type of things. Because like I said in my presentation, as you can see, once you start looking at the costs and the benefits of battery, you can shut down units without having to sit there and idle for 24/7 hours, 24/7 every day and spend all that money when you can have a battery system there protecting that asset and not spending all that money. The thing is, it's just like I mean, we look at solar. Look how far solar's come over the years. The more that the battery storage starts to show up in balancing authorities, ISOs, you name it, and they start going on the other side of the fence, you'll see the price come down. I think you guys can speak for that since you guys are the ones building them. But I mean, that's what I think we're going to see that change. It's just in this new industry, you know, we're talking about 8 years seeing all the growth, but there's going to be a lot of growth, especially, you know, we're hearing this morning talking about right now going up to the 50% mark in the California. When we hit that, no matter what, every grid operator is going to be screaming for some kind of battery storage or something else, because there's no way the generation inside California can meet that demand with all the green power. There's just no way. The intermittency and the characteristics of losing that, we see it with wind all the time in the Northwest. However, they have hydro, and hydro acts just like a battery. It can boom, it can be there. Unlike down here in Southern California, we don't have a lot of hydro. So we got to find different applications to go ahead and meet that intermittency. And I think as we go more and more, as we see more and more solar, wind, geothermal come on, you're going to see these battery storage pop up. And I think AES can point to that, just like with the projects they're doing for SCE. You're going to see these projects popping up. And the more that they pop up, the cheaper they're going to get, the more technology that's going in the batteries already from the projects I've seen in Fairbanks to now are totally changed, more efficient, and you guys can speak to that expertise on the battery side, but you're going to see a big change, I think, on the battery storage front for a grid operation aspect. I mean, it's been on the other side of the fence, like I spoke of, but you're going to see it more come to the grid and the ISOs and other stuff. There's no way around it. I just don't see where they can really prove the benefit to run a big unit, to sit there to cover these contingencies on solar, wind. So, I mean, it's just pretty much where it's at.
Yeah, and I guess you saw that our projects are clustered in some different regions, and that goes to the way the markets were structured in those regions. So we've been able to focus on areas where we could come up with a commercial structure that worked. All three of those regions have different commercial structures, so we've been able to be flexible to work with what the different locations, the grid operators and the utilities needed, and how the structuring could kind of also fit their needs and their comfort level in those different locations. So there's some flexibility there, but then potentially there's also ways that from the grid operations standpoint, you know, depending on what they're looking for and how they're structured, we could provide different products. So like the California product is a 4-hour duration battery, where most of the ones in PJM are 15-minute because of the services that they're providing and the needs of that grid.
Yeah, and on the reliability side of it, not the marketing side, but as you can see, there's been a big push for ancillary services now, and the battery is going to provide that. I mean, there's a marketability there, so if people start putting up these batteries, they're going to be able to bid the stuff in the ISO, different RTOs, whatever. So, I mean, the application's there. We just need to start building them.
Now, we are about to run out of time, but I think we could take one more question if we have, okay, we have 2 questions here. Let's see how quickly we can kind of get through the 2 questions before Tim gives me the evil eye over here. I know I'm done, got it.
I just want to ask, what is the specific product that is being purchased or sold? So, Laura, are you just buying the technology and then your engineers work it into your system, or is this effectively a fee for service? And maybe AES can speak to this too. Do you continue to own all the technology and then provide services? So what is being sold here?
So on the SDG&E side of the house, in our all-source RFO, we actually have 2 pieces to it. So we have utility-owned opportunities where we will actually work with and own the technology ourselves. And then we have the other side is a PPA, pure PPA opportunity. So we have interested parties on both sides. The utility's looking at which of the 2 make the most sense for us. I think in this changing world and how new things are, there'll be obviously a combination of both, but we are interested in owning some of it and then having some of it on a PPA basis provided to us. So that's all, without going into too much detail, those are the 2 parts of our, the RFO we have out today. I don't know if.
So all of the projects that I highlighted are owned and operated by AES. Various commercial structures, but PPA, tolling agreement, that sort of thing. But we are also actively looking at opportunities where we could sell a system to a customer that would then own it. So we're open.
So one last question here.
Now that we have smart grid is promoting distributed generation, are any of the companies that are present today planning for distributed storage, like to assist businesses and big customers to shift their loads using storage, or to help in that area?
Mark, that's probably
Well, the customer base, we're looking at a larger scale in the grid operation. Like I said, on the other side of the fence, so to speak, on the other side of the circuit, like you're talking about for a customer base, they could probably speak more to. I think they already have those application there for producers like that to offset probably their costs from the utility, so they could actually say they have solar. There's a lot of businesses now that have 1 megawatt solar type PPAs and other stuff that they're using during the day. However, like we all know, the duck curve, there's a lot of long in the afternoon, so they could actually store that in the battery where they wouldn't have to pay a cost and then run their operation at night off that battery. So, I mean, there's a lot of applications of it. That's the thing that I'm trying to get across, is the battery has so many useful applications that it can be used for. I don't think they've really been addressed or compounded or thought of, but they're there. And that's why I say once, AES and some of these other companies get them out there, which they are already starting to, you're going to see this thing unfold. And I think it's going to produce a lot of areas where we can find efficiencies to help the grid, help the customer, and bring down price.
We recently entered into this distributed energy market, so we have a new group called AES Distributed Energy, and I do think there's a lot of opportunity for behind-the-meter storage and generation and the pairing of the two. So.
And just as, if I might, almost all of our customers in the United States are behind the meter. And what we look for is, generally in this order, demand charges on the bills. We looked for KVARs, or reactive power charges. And then the last thing to go after, and it's not been economical for most people, is peaking power rates when you have time of use. But those first two generally are faster paybacks. You can run all three, and you generally do run all three. But the biggest component to the payback period is usually the demand charges.
Well, thank you all very much. Thank you to our panelists. And thank you to all of you. I think we have shown in this region that we can take on a challenge and we can be successful at that challenge. And I think we've shown that with renewable energy, and I think we have an opportunity to do the same now going forward with energy storage and electric vehicles. If you haven't bought your electric vehicle, a lot of great options out there. So anyway, thank you all very much.